Okay, so we're now going to focus our attention on work. Okay, we defined before that work is a change in energy of a system. Okay, so now we're going to focus on how can we do that starting with from kinematics. You can do some calculus to show this, derive this as a result. The calculus itself is not important to us, but the result is. And so we can use those ideas to show that the work depends on how hard you push on something, which makes sense. You know, if I push harder, I feel like I'm doing more work, but also how far the object goes while you're pushing on it. Okay, and you can kind of make sense, like if I've got someone sitting on a cart and I start pushing them down the hallway, the longer I'm in contact with them, the more that force is actually causing the acceleration, so it's speeding up more and more. Okay, and so we can define work. The work then ends up being the definition of work ends up giving us that it is equal to force times this distance traveled. Okay, so let's take some examples. All right, so let's suppose we have this box right here. Okay, and I push it with 100 Newton force, and it goes 1 meter. Okay, so that's that 1 meter right here. Okay, and so if I calculate it, well, the work done is just simply the force times the distance traveled. So that's 100 newtons push force, 1 meter distance, and I get 100 Newton meters. Okay, but the SI unit for that, a Newton meter, is the same thing as a joule. Okay, so Newton meter equals a joule. All right, so in other words, distance times, or force times distance, is also a unit of energy. All right, so that's a basic example. Now, some things about signs is if I push on it in the same direction it goes, which is what you'd think, oh, doesn't that happen all the time? But I'll give you an example of the opposite. But if I push on in the same direction that it goes, then the work is positive. Okay, that kind of would make sense. Let's say I'm pushing someone on a cart down a hallway. Well, they're going to speed up if I push in the same direction. So they're gaining kinetic energy. All right, well, what about if I push in the direction opposite the direction they're moving? Like, well, who would do that? Well, what if this person's going really fast and they want to slow down? Well, they might stick their hands down and drag them on the floor. So there's this backwards force on the floor. Or maybe there's a rope hanging back and I'm standing there behind them and I pull on it, but I don't want to jerk it and make them fall off, and so I have to kind of run with it, slowing them down as they go. Okay, so that starts to make sense. So the force would be in one direction, opposite their motion, while they move opposite that force. Okay, so if that's the case, we define work to be negative or less than 0. And again, it makes sense. Their kinetic energy would decrease. Okay, so those are a few ideas that are important. The direction, if they're in the same direction, we get positive. If they're opposite direction, we get negative. And ultimately, that work is force times the distance. Okay, so let's go back now. We introduced last time that the ATP energy, when it gets turned from ATP to ADP, that we can get about 43.2 zeptojoules out of it. And we mentioned that zeptojoules is the same thing as a piconewton nanometer. Well, here we can see a little bit better why that's the case. Okay, because piconewton is the size of the force and nanometer is the distance traveled. And that's how work is defined, force times the distance. Okay, now this becomes very useful. This piconewton nanometer becomes useful because, as we mentioned, that the size of molecules are on the nanometer size. The distances they step are on the nanometer size, and the forces they apply are on the piconewton side. So that makes more sense. So that's a useful unit for thinking about chemical energies that are doing work, that are doing something. Okay, so I've got a few examples here that I think are pretty cool. All right, first one is our kinesin molecule. So let's find out what the work done by kinesin through 1 ATP. Okay, so if you do a Google search for the force of kinesin, it's got a range, but we'll just pick this 5 piconewtons. It's kind of in the middle of the range. Okay, so it can apply about 5 piconewtons of force, and it steps 8.1 nanometers every time. Now that step comes from its highway, what it can step on. It steps on microtubules, and it goes between every same type of molecule called tubulin. Okay, so it'll step on the same type. All right, and those those distances are very fixed. So its distance is very fixed. The force it applies, it depends on environmental conditions. Sometimes temperature, sometimes other things. What's being pulled on it. But on average, about a middle of the range values is 5 piconewtons. Okay, so having said that, then what we have is if you multiply the 5 times the 8 in piconewton nanometers, it's going to give you this 40 zeptojoules or 40 piconewton nanometers. Okay, and so that's on the order of ATP, but a little less, which is good, because if it was a little more, that means it couldn't do that step with 1 ATP. It takes ATP to do this, and the biggest thing is that energy transfers and transformations need to be consistent. So this says that when you hydrolyze 1 ATP or transition, so hydrolyze means ATP to ADP, when you hydrolyze 1 ATP, you have the ability to get 43.2 piconewton nanometers out of it. Okay, this kinesin molecule was able to get almost that amount. Okay, almost that amount, but not quite. And that makes sense because you're not going to get all that out. Sometimes there's some fluctuations, thermal energy, you contribute to thermal energy. Sometimes it takes a little bit of that ATP energy to cause the protein to fold itself, to make a change inside the protein. So you're not going to get all of that energy out, but it's awfully good. It's a pretty high percentage. I mean, we're talking over 90%. Okay, so this is a really, really efficient motor. All right, now let's turn to one of my favorites, the Phe29 motor. I've drawn it over here on the side, okay? And what it is, it's got this kind of geodesic shell, and it's got this ring below it. That's the motor, and it actually has these arms made out of RNA that actually bend and do stuff. It's pretty cool, but it's a discussion for another day. But basically, the goal of that motor is to pull the DNA inside it. Okay, so the way you figure out how much work it can do is to figure out the force it applies and how far a DNA gets pulled into it. Okay, now there's some really cool studies that show that each arm of the motor pulls the DNA in 2.5 BP, which is base pairs. Now, what's a base pair? Each one of these, so over here on, it's hard to see with that color, over there on the, I'm going to change color here, over here, okay, each one of those lines in that DNA molecule is a base pair, okay, the two sides of the double helix, okay, and so when you're dealing with DNA translocation or moving DNA, it's more efficient to think about how many base pairs can you move. And so each one of the arms of this Phe29 motor can move 2.5 base pairs in one stroke. Okay. Now for us, we care a little bit more about how the physical distance, so how many nanometers. And if you look up, a base pair is 0.34 nanometers wide, or 10 base pairs is 3.4 nanometers. Okay, so if you do that little conversion there, then you end up with 48 zeptojoules, which is on the same order of ATP, but there's a problem. It can't be more than ATP. How do we get more work done than the energy in? Okay, you at best can get equal, but usually you lose some to thermal energy and other things. So what's wrong here? Okay, so I'm going to come and fix that and show why is that not true? Why is this 48 actually not true? Again, really cool discussion. We could have a whole day just talking about the motor function of this V29. But there are actually inside this motor there are 5 units. There are 5 arms. Okay, and there are 5 arms that grab the DNA and pull it in. And they each take a turn. Okay, but one of the 5 arms has a specific role of holding the DNA so it doesn't slip out. One thing that's cool about this motor is that the DNA gets packed crazy tight and makes this outward force. It's trying to push back out so it won't let more come in. So you have to hold on to it tight at all times. Okay, and so one of those 5 motors actually holds on, and it takes ATP for it to hold on. And so only 4 arms actually pull it inward. Okay, so a better way of doing this is if you take this work done, and this is instead not the work done by 1 ATP, but if you take that times 4, okay, it's the work done by 4 motors, but it takes 5 ATP. Okay, so this is what we thought. Oops, let me change my. This is what we thought. Why is it not going back? There we go. This is what we thought it was per ATP, but it actually is it has 4 strokes, so that's per stroke. Okay, but it takes 5 ATP to do it because the one arm doesn't pull, it just holds on. And so to check that, we see that 4 times that number gives us 194 zeptojoules, but if we divide it by the 5 ATP, then we end up with 38.8 zeptojoules per ATP, which then is consistent with our rules that you can't create energy. The energy has to convert one form to another or be transferred in from an outside source. So that now makes sense because it's consistent with what we know. All right, now power. Okay, so we've talked about work done. Oh, sorry, we need to go back. I want to talk about the myosin. So just as another example, myosin, remember, it's a molecule that walks along actin. Actin is a different fiber in the cell. Particularly, it's interesting because it's also in your muscles, and myosin works on the muscles to pull. Okay, so that's interesting. But you can see that it's not it doesn't do as much work as kinesin does. It's got a much smaller, or a relatively small pulling force, though it's got a bigger step. So the units on the actin are further apart, so its step is bigger, but its pulling force is smaller. Okay, so now let's go and talk about power. All right, things like Newton's second law is a definition of nature. We observe nature and wrote out what we observed, and we get Newton's second law. Same thing with kinematics. We observe nature and we put variables to it and define, or we explain how nature works based on that. Power is a definition. We instead say we're going to define something we observe. All right, or we're going to define something from things we observe. So that's what the 3 lines here mean. It's not just equals, it's defined as. So it is equal to in magnitude or in size, but we're defining it. Okay, so the power is defined as a change in energy over a change in time. Okay, and if we put in what we know about energy, well, energy is changed when you do work on it. Okay, well, what do we know about work now? Work is a force times a distance. Okay, and so all of these are fine definitions, just depending on maybe what we know, what we're starting with. Okay, but what's cool here is that a change in position over a change in time is something we already know. It's a velocity. So we can instead say this is a force times a velocity, which works out to be very easy to use because often we can see how fast something's going, even though we can't resolve it single steps or the time per step. We can figure that out. And so we can observe velocity fairly easily. All right, so that's a great definition of power. But remember, all of these are great definitions. It just depends on what you know. So if you know the energy change, well, use that one. If you know the work done, use that one. If you know the force and the distance traveled, use the third one. Okay, so that's the definition of power. Now, how do we apply this? Okay, so looking back at some of our examples, kinesin. If you look up what its velocity is, how fast does it move along a microtubule, then it's about 0.02 to 2 nanometers per millisecond. And again, I chose nanometers because that's kind of our characteristic size. And milliseconds is kind of the characteristic time of molecular interactions. Microsecond to millisecond, depending on what we're talking about. Okay, now remember, it was the force it applies is about 5 piconewtons. All right, and so if we apply this equation, the power then is going to give us about 0.1 to 10 piconewton nanometers, that's the energy side, per millisecond. Okay, so power is a rate of change of energy. Now, if you're into engines and motors and such, then another way of talking about power is horsepower. Okay, and so a horsepower is not a convenient unit for molecules. As you can see, that's the same thing as 13.4 zepto horsepower. So very small horsepower. Okay, but if we look at a comparative size scaling, so this car right here is my youngest son's and my dream car. Okay, it's a Corvette C8, and it has about 450 horsepower stock, and the car weighs about 1,700 kilograms. So, and it's a beautiful blue. All right, so that's the horsepower from the 1,700 kilogram car. All right, now if we look at our kinesin molecule, here's our kinesin molecule. Well, it weighs 1.66 times 10 negative 22 kilograms. So that is 0.16 zeptogram or zeptokilograms. Okay, which kind of doesn't make too much sense, but since kilograms the SI unit, I want to reference that. So it's crazy small, and it has a crazy small power. So my question is, how much would this kinesin molecule have to weigh to have the same power as this Corvette? And the halfway hidden answer is it only have to weigh 6 kilograms. This kinesin, if we scaled it up, and everything was able to scale the same, if we scaled it up by mass, then it would only have to weigh 6 kilograms in order to have the same horsepower as this Corvette car, which is pretty crazy, because most of that 1,700 kilograms is in the engine. Okay, well, not most, but a large fraction of it is in the engine. And so our engine right here of this molecule is quite strong, or is able to deliver quite a bit of energy in time. Has a lot of power. Okay, I will pause there, and we'll use these other two examples for some class discussion.